The western coast of Norway has been dismantling human ambition for over 1,000 years. Viking longships, the most advanced watercraft of the medieval world, were routinely splintered against the granite walls of these fjords by storms that arrived without warning and left nothing behind but driftwood and drowning men. For centuries after, fishing vessels, trade ships, and ferries have been swallowed by the same merciless corridor of deep water, howling wind, and North Atlantic fury that separates the coastal cities of Bergen and Stavanger. The fjords themselves, monstrous glacial trenches carved over 40 ice ages into the bedrock of the Scandinavian shield, plunge to depths that make conventional bridge foundations a physical impossibility. The Sognefjord descends over 1,300 meters below the surface. The Bjørnafjorden, a 5-kilometer gash of open water sitting directly in the path of the North Sea's most violent storm systems, drops 550 meters straight into darkness. No pier has ever touched the bottom of a Norwegian fjord. No piling has ever been driven into that abyss. For a millennium, the geography has dictated a single, humiliating verdict. You do not cross these waters on anything permanent. You cross them on a ferry, or you do not cross them at all. Logic, economics, and the accumulated engineering wisdom of centuries all converge on the same rational conclusion. Do not attempt a fixed crossing here. The water is too deep for conventional bridge piers. The seabed is layered with soft glacial sediment that swallows anchors and shifts under load. Winter storms from the North Sea hurl waves of 3 to 6 meters against anything standing above the waterline, driven by sustained gale-force winds that can change direction in minutes. And the history of floating bridges, the only structural category even theoretically capable of spanning such depths, is littered with catastrophe. In 1979, the Hood Canal Bridge in Washington state was ripped apart by 80-mile-per-hour winds that tore open its pontoon hatches and sank an entire section of the roadway into the sea. In 1990, the Lacey V. Murrow Bridge, a floating structure spanning Lake Washington, folded into a massive V-shape and sank during a Thanksgiving storm after compromised pontoons flooded with water. Floating bridges do not merely face risks. They have a documented history of being destroyed by the very environments they were designed to survive. Yet the Norwegian government, backed by the full institutional weight of the Norwegian Public Roads Administration, has decided to do what no civilization in history has ever accomplished. They will build a floating bridge across the open waters of the Bjørnafjorden, 5.5 kilometers of roadway suspended on approximately 40 colossal steel pontoons, curved deliberately against the prevailing winds, anchored to a seabed 550 meters below, and designed to endure 100-year storms for a service life of 1 century. It will be the longest floating bridge ever constructed on the surface of the Earth, and it is merely one component of the most audacious highway project in human history. The ferry-free E39, a 47 billion euro campaign to eliminate 7 major ferry crossings along Norway's 1,100-kilometer western coast. They are not building a bridge. They are declaring war on a geography that has been winning for 10,000 years. This is the story of how Norway is attempting to erase 7 fjords from its transportation map, pouring tens of billions of euros into the most hostile marine environment in Western Europe, and constructing a floating bridge so unprecedented in scale and engineering ambition that it has no historical parallel, gambling that human ingenuity can finally outperform the North Atlantic storms, the glacial depths, and the relentless corrosive chemistry of salt water that have been defeating every structure placed in their path since the age of the Vikings. To feel the true hostility of the Bjørnafjorden, you must abandon every touristic image of serene Norwegian waterways and confront the environment as the engineers see it. This is not a sheltered inlet. This is an exposed 5-kilometer-wide channel positioned at the juncture where the deep, protected waters of the inner fjord system meet the full unobstructed fury of the North Sea. Winter low-pressure systems barrel across the North Atlantic and funnel directly into this corridor, generating sustained gale-force winds and wave heights that can exceed 6 meters in a matter of hours. The water column beneath the surface drops to 550 meters into darkness. The seabed itself is a treacherous stratum of soft glacial clay and compacted moraine sediment deposited during the last ice age, material that behaves unpredictably under the dynamic loading of anchor cables subjected to storm forces. And the water chemistry is an aggressive cocktail of North Sea salinity that corrodes unprotected structural steel at rates of up to 0.5 millimeter per year, while biofouling organisms colonize every submerged surface within weeks, adding parasitic weight and accelerating degradation. This is not a construction site. This is an active, multi-vector assault course designed by geology, meteorology, and marine chemistry to annihilate anything permanent. The economic and strategic desperation behind this project is staggering in its clarity. Norway's western coast produces approximately 60% of the nation's export goods, petroleum, seafood, maritime technology, and advanced manufacturing. Yet the transportation artery connecting these economic engines is fractured by 7 unbridged fjords requiring ferry crossings. The current journey along the E39 from Kristiansand to Trondheim takes 21 hours, a drive that should take half that time on a modern highway network. Every ferry wait, every weather-related cancellation, every hour of lost transit time bleeds billions of kroner from the regional economy annually. Supply chains fracture at every crossing. For a nation whose sovereign wealth fund exceeds $1.7 trillion, the absurdity of operating a medieval ferry system to move goods along its most productive coastline is not merely inconvenient, it is an act of economic self-sabotage. The weapon designed to defeat the Bjørnafjorden is a structural concept that exists nowhere else on Earth at this scale, an end-anchored, curved floating bridge. The curvature is not aesthetic, it is a calculated structural decision. A straight floating bridge spanning 5.5 kilometers would be fatally vulnerable to lateral wind loads and thermal expansion forces that could buckle or crack the deck structure. By curving the bridge in a deliberate arc, engineers transform destructive lateral forces into compressive forces that the structure can absorb, distributing stress across the entire length rather than concentrating it at weak points. The bridge will ride on approximately 40 massive steel pontoons, each one engineered to provide buoyancy while remaining anchored to the fjord floor by a sophisticated mooring system of tension cables designed with enough elasticity to accommodate tidal fluctuations, storm surges, and the dynamic heaving of wave action without snapping. At the southern end, a cable-stayed high bridge section will rise to provide 50 meters of vertical clearance for international shipping traffic, a soaring gateway between the floating roadway and solid ground. The entire structure is engineered to survive a catastrophic scenario that floating bridges have historically failed. A vessel collision event followed immediately by a 100-year storm. Not one disaster, 2 simultaneous disasters. And the bridge must stand through both. The numbers obliterate every reference point in floating bridge engineering. The Bjørnafjorden crossing will stretch 5.5 kilometers, more than double the length of the current world record holder, the SR 520 bridge in Seattle, which spans 2.35 kilometers across Lake Washington. The Norwegian bridge will consume tens of thousands of tons of structural steel. 40 pontoons, each one a watertight steel vessel, will be positioned at intervals of approximately 100 to 120 meters along the bridge alignment. The mooring system will extend cables from these pontoons to anchor points on a seabed 550 meters below, a depth at which the water pressure alone exerts crushing force on every component. The Hordfast Link, the larger infrastructure project of which this bridge is the centerpiece, carries a current estimated budget of 53.7 billion Norwegian kroner, approximately 5 billion euros for a single highway connection. And the Bjørnafjorden crossing is just one of 7 fjord crossings that the ferry-free E39 must defeat. The total program cost has been estimated between 33 and 47 billion euros, a figure that would rank it among the most expensive infrastructure investments in the history of Western Europe. The broader E39 campaign has already produced its first act of engineering defiance. The Rogfast Tunnel, a 27-kilometer subsea road tunnel burrowing beneath the Bjørnafjorden at a maximum depth of 392 meters, is currently under construction and scheduled to open in 2033. When completed, it will be the longest and deepest underwater road tunnel on the planet, proof that Norway is not merely studying the problem but actively drilling, blasting, and tunneling through the geology that has imprisoned its coastline for millennia. The Rogfast has already confronted the mountain's resistance, complex rock formations, massive groundwater infiltration requiring continuous pumping, and the relentless geological pressure of hundreds of meters of seabed bearing down on every meter of excavated tunnel. Ventilation shafts on the island of Kvitsøy have been completed. The boring machines advance. But the ocean has not surrendered a single meter voluntarily. Then comes the confrontation that every floating bridge engineer quietly dreads. The Bjørnafjorden is not Lake Washington. The storms that sank the Hood Canal Bridge and the Lacey Murrow Bridge were freshwater events on semi-protected bodies of water, violent but fundamentally limited in the forces they could generate. The North Sea does not operate under those constraints. Cyclonic winter storms track directly across the open Atlantic and compress into the fjord corridor, generating combined wind and wave loading scenarios that no floating bridge has ever been asked to survive. Engineers at SINTEF Ocean have subjected scale models to thousands of simulated storm conditions, measuring pontoon displacement, cable tension, and structural resonance frequencies to identify and hopefully prevent the catastrophic failure modes that have historically destroyed floating structures. The critical vulnerability is simple and terrifying. If wave energy couples with the bridge's natural resonance frequency, oscillations amplify exponentially until structural members fracture. The curved alignment, the pontoon spacing, and the mooring cable elasticity have all been calibrated to break this resonance cycle. But calibration in a laboratory tank and survival in a North Atlantic gale are separated by a gap that only time and weather can close. Fast forward to the present. The Rogfast tunnel bores deeper. The Hordfast regulatory process grinds through Norwegian parliamentary procedure. The Bjørnafjorden Bridge remains an advanced engineering development, studied, modeled, simulated, stress-tested in every computational environment available to modern engineering, but not yet built. And this is the haunting reality of the project's current phase. The world's most sophisticated floating bridge exists today as mathematics, as finite element analysis, as computational fluid dynamics, as tank test data from SINTEF. The steel has not been cut, the pontoons have not been welded, the cables have not been tensioned against a seabed 550 meters below. The North Sea has not yet had the opportunity to test whether the equations are correct. The paradox cuts through every layer of the project. To the Norwegian commuter who currently waits 45 minutes for a ferry across the Bjørnafjorden, this bridge is liberation, the end of a geographic humiliation that has fragmented their coastline since the ice retreated. To the structural engineer who must guarantee that 40 steel pontoons anchored at 550 meters will survive a century of North Atlantic punishment without a single catastrophic failure, the bridge is something altogether different. A 5.5-kilometer experiment in trusting calculations that have never been validated at this scale, in this environment, against these forces. The distance between the commuter's impatience and the engineer's insomnia is as deep as the fjord itself. Floating bridge engineering on this scale is not an act of mastery. It is the most expensive, most calculated, most technologically audacious form of negotiation ever conducted with the open sea, a treaty written in steel and mooring cable, stipulating that the ocean will permit a roadway to exist on its surface in exchange for a perpetual payment of maintenance, inspection, corrosion management, the quiet, permanent acceptance that every pontoon, every anchor, and every welded joint is operating under borrowed time. They are curving a highway across 5.5 kilometers of open fjord. They are anchoring it to a seabed deeper than most skyscrapers are tall. And they are betting that the storms that have been shredding this coastline since the glaciers carved it will choose, for the first time in geological history, to cooperate, because sometimes stretched across the most violent waters in Western Europe, suspended on 40 steel vessels floating above a glacial abyss that no foundation has ever touched, there is a vast, silent, terrifyingly beautiful wager. A wager between humanity's refusal to accept a geography that keeps its cities apart, the North Atlantic's ancient, indifferent, storm-driven campaign to keep them that way, and the tens of billions of euros, the decades of engineering, and the reputations of an entire nation's infrastructure establishment that are now staked, openly, irrevocably, and with no precedent for comfort, on whether steel and mathematics can hold a road above water that has been swallowing ships for 1,000 years.